Experiencing technical difficulties. It shouldn't be. Okay.
Oh no, it's not working. We should cancel class.
Yeah. We're gonna get it. Here we go. Okay. I got it. Here we go. 30 seconds in. So you guys have a review day on Monday and a test on Tuesday. We learned synthetic division yesterday. And in addition to our box method and long division method, we learned synthetic division, which is certainly the easiest, but it has limitations. And so, hi, can I help you? Who? Avery? There, yeah. It does have limitations, so we can only use synthetic division when we have a coefficient of 1 on the factor, all right? And so we want to, as a little warm-up here, let's just start at number 2. Consider the polynomial function. We want to divide the function by x equals 9. So since it is a 1x, we can use synthetic division. And what goes on the outside of my little synthetic division box? A 9, a positive 9. And then what should we write across the top of our box? Is that right? 0, 0. We have a 0x squared term that is missing. And so we definitely need to fill in, you can grab that, fill in that 0 term that is missing. And then the 9 and the negative 80. All right. We are going to bring down the 7 and then multiply. What do we get? 63 and combine 0 and multiply 0 and combine we get 0. Multiply we get 0. Combine we get 9. Multiply we get, and combine we get a remainder of 1. So our division, our quotient is 7x to what power? X to the third. And again, because we started with x to the fourth, and we're dividing out an x, that must decrease to a third. All right, and so 7x cubed plus 0x squared plus 0x plus 9 plus 1 over x minus 9. Okay. We also want to find f of 9. What does this mean, f of 9? 9 plugged into all the x's. Yeah, you can see it's a direct replacement here. We have f, and it's saying put the 9 in place of the x. So this is going to be 7 times 9 to the fourth minus 63 times 9 cubed plus 9 times 9 minus the 80. Will you plug that out in your calculator, please? What'd you get? Ooh, there's a mistake somewhere. 1. Hey! You got 1 as well. Uh-huh. All right. So, well, that's interesting. What do you notice? It's the remainder. Whatever you plug in, when you evaluate a function, it also corresponds to the remainder when you use division on. It's kind of interesting, yeah? So here, this is the remainder theorem. And it says, if a polynomial function is divided by x minus a constant, then the remainder happens to be exactly the same as the function with the constant plugged in for x. So that if you replace the constant and with the x, you'll get the same value. Kind of interesting. And so this is actually called So using synthetic division to evaluate a function. So this has been done for hundreds and hundreds of years. They learned really early on that to do this calculation out is quite challenging, right? Like 9 to the 4th power. I don't have that memorized, do you, right? So to actually figure this out, and this is, before calculators, right? They figured out this pattern and said, hey, if I want to evaluate a function, then I can use this method and we'll get the same thing. And that's kind of cool. And so that synthetic division to evaluate a function is called synthetic substitution. And so we can, in fact, use this process to quickly evaluate really complex polynomials. And so use the remainder theorem, hashtag synthetic substitution, to evaluate the function at C. And so here I want to use, here's my C. So we're going to substitute in that C value using synthetic substitution. So we use the exact same value. You'll notice this is not in bubble form, okay? It's just the value. And we can use this 1, 8, 12, -7, -14. And it's just a really fast method to actually evaluate the function. So bring down your 1, multiply, combine, multiply, combine, multiply, combine, multiply, combine. All right? And so very quickly, you can, and God, that is so much easier, right? Like when you think about how easy this was and how fast this was for me, rather than having to go to my calculator and plug all of this in, like this is just super fly. So f of -3 equals -20. Guess what? When we have this, again, it is an ordered pair. It is a point on our curve. So this was how they used to have to do stuff all the time. If they wanted to graph the curve, they would have done synthetic substitution to get like 50 ordered pairs so that they can then plot the curve and see what shape it is. So math, once upon a time, had a lot of work, all right? A lot involved to figure out what does this look like when we graph it. And this is how they would have done it, which is a really kind of cool thing, this method of substitution. Let's turn the page. Oh, is that all I did? Oh, yep. Okay, cool. Sorry, no, all right, turn them, here we go. Do you need another one of those? I don't think so, right? It's pretty easy, yeah? Okay. So the factor theorem is a sort of, hey, which we sort of talked about briefly yesterday. What happens if we evaluate a function and it has a remainder of 0? And so for, we can use synthetic substitution to evaluate our functions and get all these ordered pairs. But then it turns out when we have that remainder of 0, well, that again, if that's an ordered pair and maybe like, we maybe get f of 3 equals 0. Well, 3, that's an ordered pair, 3, 0, 1, 2, 3. It happens to be a 0 of our function, right? And so anytime we use that synthetic substitution and we get a remainder of 0, it turns out that that's giving us one of our factors, which is really kind of nice. So given, all right, so the factor theorem says x minus c is a factor of f of x if and only if and only if f of c equals 0. That really means it has a remainder of 0, and as I mentioned yesterday, factors divide evenly. 3 goes into 24 8 times, remainder 0. And it gives us a really good point on our graph, those points that we're always interested in. So we want to know, use the factor theorem to determine which binomials are factors of the given function. We are not going to do this very often. This is not something I believe in doing. But let's see here. I want to know if x plus 1 is a factor. So what I'm going to do is I'm going to use my little synthetic substitution here. This is in bubble form. What number should go on the outside? -1. And so I'm going to use my little synthetic here. 1, 0, -31, 30. Did you remember the 0? All right. So bring down the 1, multiply. We get -1, combine, multiply, combine, multiply. We get 60. All right, not a factor. So x plus 1 is not a factor because it doesn't have a remainder of 0. All right. Let's try the next bubble. X minus 5, what should we use on our +5? Good. So 1, 0, -31, 30. All right, so bring down, there you go, 1, multiply, combine, multiply, combine, multiply. Hey! We got a remainder? 0? Which means x minus 5 is a factor because it has a remainder of 0. Yay! Let's try one more. What should we use for the last one? -6, 1, 0, -31, 30. Bring down the 1, multiply, combine, multiply, combine, multiply. Hey! What do we get? A 0. Remainder 0 happens to be a 0. That's why we call them zeros. So x plus 6 is a factor as well. Now, that's great and all, but again, this is the 21st century, not the 15th century. So, while it's lovely that we have that technique, can't we just graph it? My favorite phrase, when in doubt, graph it out, because you can learn a ton. Oops-a-daisy, that's not going to do okay. Oh, that's a minus. Okay. We can do a ton with our calculators. And so, again, if I'm looking and I want to know if 1 is a factor, then I should have the ordered pair -1, 0, or 5, 0, or -6, 0 on my graph is really the question there. And I can use trace to double check. And just typing in the x value, -1, I get 60. Clearly not an x-intercept, clearly not a 0. If I plug in a 5, there it is, I get a 0. That means x minus 5 is definitely a factor. And of course, if I plug in -6, there it is, we get a 0. So we can do a lot of this stuff graphically as well. But I wanted you to know that that is an option. But again, our goal is always factoring. So let's go down here to factoring and finding zeros. We want to use the factor theorem and the given binomial to completely factor the polynomial function and then give the zeros. So again, here they're telling us that x plus 3 is a factor. And so we're going to use some synthetic division. What should I use on the outside? -3. We got a 1, a 3, a -4, and a -12. And we're going to bring down the 1 and multiply and combine, and multiply and combine, and multiply and combine. And so we want to write this polynomial, the whole polynomial, as a product of factors. So the first factor they told us was x plus 3, and it was a factor. And what is the leftover quotient there? -4, good. X squared minus 4, put it back in a polynomial form. And then from there we can double bubble Always, always. So we get x plus 2 and x minus 2. So this is fully factored, completely factor. That was the goal. So this is completely factored. And what are our zeros? Plus or minus 2 and negative 3. All right. Good. All right. Any questions on that? No? All right. This is the whole goal here, really, being able to factor. Let's go down and look at, like number 7. Number 7. They give us a factor of x plus 5, which means in synthetic I can use minus 5. Good. So we have a 3, a 5, a negative 42, a 40, and a 0. We need that constant term as well. Very good. Bring down the 3. Multiply, combine. Multiply, combine. Multiply, combine. Multiply, combine. So because it has a remainder 0, that definitely means x plus 5 is a factor. So my polynomial function can be rewritten as the factor x plus 5 times what quotient? 3x to the third. Yeah, we started with x to the fourth, and we're dividing out an x. So we're removing one of them, so that becomes x to the third. And then minus 10x squared plus 8x. All right, and then what can we do with this trinomial? GCF, sure. I'm going to pull that x way to the head of the class there, all the way out in front. And if I take out that x, then I'll have 3x squared minus 10x plus the 8. And here we can double bubble the hard trinomial, but that's okay. All right. 3x times 1x is our only option to get that 3x squared. 3x times 1x, that's the only option. Last times last has to be positive 8. 3 and 2 is 6.
4 and 2.
Oh, 4 and 2. That will work better. Negative 4 and negative 2. Also 8 and 1. Negative 1 rather. 8, negative 8 and negative 1 is an option. But negative 4 and negative 2. Let's see. I want that minus 4 on the outside and the minus 2 on the inside. How do we know if we did this right? In and out. Check the... Oh, did I totally flip that around in my head? Yeah, okay. So minus 4 and plus 2. Sorry about that. Yeah, thank you. Sorry. All right. They both have to be the same sign. They both have to be negative. Negative times negative gets me the positive 8. All right, let's check here. So I'm going to check my outside and inside. So I have 3 times negative 2 is negative 6x. And then negative 4 times 1 is negative 4x. And yay, that does give me that middle term, that negative 10x. Okay, thank you guys. All right, so this is fully factored then. Completely factored form there. And what are our zeros? Positive 4/3. Very good. Good. Again, 3x minus 4 gets that equal to 0. And then we would have to add the 4 and then divide by the 3 to get that 0. And so that's what we're doing. We are factoring. Yay! Do you have questions for me? No. Okay. Happy Friday. I don't know. Let me look. Okay. Is it still? Oh, I missed.